Wow, that was a good way to wake up. Good morning. How's everybody doing today? Happy Valentine's Day. Welcome in the chat. How are you? So today we're starting chapter 15, chirality. And so let's go over some couple of definitions. So let's start off with isomers. So what are isomers? We should know from kind of our previous chapters. Looking for answers in the chat. And so isomers, let's just broadly define as different compounds with the same chemical formula and so we have been mainly focusing on structural or constitutional isomers. And so you've had some practice with these in the previous chapter. And so again, they're going to have the same formula, but different connectivity and even different functional groups. And so some of those isomers we looked up, it could be dimethyl ether, so this of course contains an ether, so C2H6O, or we could also do this, and so this is ethanol, so C2H123456O, so constitutional isomers. And then do you remember the next type of isomer or another type? Let's do some pink for Valentine's Day. And so last we have stereoisomers. And so these differ in 3D arrangement. So some of the ones we've looked at earlier were the cis versus trans isomers. So transbutene versus cis-butene. And we saw with our structures that we couldn't have rotation. And so now let's look at kind of our next bit. Start a new page. So what does it mean to have chirality? So what does it mean to be chiral or achiral? Well, first of all, let's look at what it means to be an enantiomer. So an enantiomer is a non-superimposable, welcome in the chat, now I'm taking questions at any time, so ask questions about anything, preferably chemistry related. And so often, let's just start with our hands. So our hands are considered non-superimposable mirror images. So no matter what you do, right, you can't get your hands to be superimposable. So they are, right, mirror images. So there is a mirror plane. And so let's look at this with molecules. So you did this probably in lab. So there we're just starting out with 2 molecules of methane. And so the concept of chirality doesn't come into play, if you remember, until we have 4 different substituents. And so that's part of chirality, because right now we can rotate this. They're all the same. Let's replace one of the hydrogens on each of these with a green ball. This could represent a halogen. And so now, right, they're still the same. They're still identical by rotation. They could be superimposed. So let's swap out another one. I was just trying to pick colors. Let's go with red. So there's one red one, and I'm just picking them at random. And so those are still identical by rotation. You can switch some of the bonds if you don't believe me. So I just took out. And you can still rotate it so that they are superimposable. So right now, right, they're still identical. And so I'm going to write this down for a second. So CH2 XY, right, no chiral center. So you have to have 4 unique things on there. Apologize. As winter winds down and we head towards spring allergies are a thing for me. All right, so I'm going to replace the top ball on this one with a yellow one. And then I'll replace this side one with a yellow one. And then we'll see, are they still superimposable or not? And, and so not quite, right? So now they do look like mirror images. So we could rearrange them like this. So now we have a mirror plane. And so now we have a chiral center. And so let's write that down. So carbon bonded to 4 unique groups is a chiral center. Let's draw this. And so now we have our CH XYZ molecule here. And so I'll just draw, let me switch colors. So we can draw our molecule. And I highly recommend some sort of kit for this part. If you don't have, a proper molecule kit, you can just take like from the craft store little styrofoam things and start putting toothpicks in them, and that would work. And so I just want to draw this. So atom Z here. Z, now I'm just drawing kind of my 3D shape. So X, so this is all in the plane of the board. Then let's show our stereochemistry. Oh, sorry, this should have been a wedge since it's coming out of the plane of the board. And then our hydrogens. And so now we can draw our mirror plane. So again, these are mirror images of each other. We can see that here. They are just not super imposable mirror images. And so part of identifying a chiral center is looking at the carbon and then does it have any symmetry or not? Does it have 4 unique groups or not? So we'll be kind of practicing that. And so let's pick some molecules. So now we want to be able to find chiral centers. So let's start with, this is from your book. I just got a different picture of it. So let's start with albuterol. So can you find the chiral centers here? So take a minute or two. See if we can find the chiral center. So going through, you have to kind of find, what is your carbon that has 4 unique things attached to it. So of course this carbon has 2 hydrogens, so that's not it. This one only has 3 things, okay, so that wouldn't work. So those aren't chiral centers. But what about this one? So we have, right, a hydrogen. And so that does give us 4 unique things. So this branch is unique compared to this branch. So this looks good. And any other chiral centers here? So it has to be carbon. And so there's our chiral center. And so I just wanted to show you this 3D picture because now this tells you, so this is your chiral center, that OH. So we have it facing this way for one of them. So this would be R and the center here. And this is S, chirality at the bottom. So albuterol is a commonly used medication. So I believe it's some sort of bronchodilator. And so it is sold as the racemic mixture. So again, there's a depiction of the chiral center there. And so it does, it is formed as a racemic mixture. And this is another interesting thing. So the compound undergoes racemization. So basically it can change forms, but it's not stable. I just don't want to draw all these drugs. Let's try another one. So this one is Prozac. That was a terrible image quality. So where is the chiral center in this one? Give everyone a minute to look at it. chiral center. So it would be here. So we have this carbon here with a quarks hydrogen and 4 different things attached to it. So let's look at another one. Trying to find an image that doesn't give away where its chiral center is at. Oh, so let's look at this next one. So this is thalidomide. And so this is kind of why our chiral center is important. And so we have our chiral center here. So this is our carbon. And even though this is a ring, this still counts as a unique chiral center. So you have like this side that has your ketone and amine on this side, and this one does not. So that makes it unique. And so let me write down what this compound was. And so I'm bringing your attention to this one since, let me double check. I believe it was the R chirality that is used. Yes, so the R form is the bioactive form. So this was used as like an anti-nausea drug in pregnancy. It's also used as a variety of functions still today. And so why this drug has gotten famous is that pregnant women took the drug and then their babies had birth defects. And so they later found that this drug, while the R1 is the one that is desirable, it racemizes, and so it's available as a racemic mixture of the two. And even in your body, it can get racemized and converted to the unsafe form. And so that's kind of, the tricky part about drug development is these chiral centers are often needed because of the activity, since they fit in some certain way. But, the other form could have different unintended side effects. So let's look at kind of some more chiral centers here. So chiral center? Yes or no? So you might be tempted to think that this carbon is a chiral center. It has 4 things attached to it, but it does have a plane of symmetry here, right? So this branch is the same as this branch. So this is not chiral, but we could change it. And now it is chiral. So repeat that. not chiral, right? Symmetric, not chiral. Chiral center, because now this is asymmetric. Well, let's look at, this is another good one for how many chiral centers. So how many chiral centers are there? So let's examine this. So we have, so this is a carbon with 4 things attached to it, right? There's a hydrogen. This is a carbon with 4 things attached to it. And then what about this one? And so if we look, let's look at them one at a time. And actually, this is not a chiral center. Let's make it a chiral center. Chlorine, chlorine, there we go. And so now this would be a chiral center if this is a chlorine, carbon, methyl, other R group. So that works. Same with this one. So that's a chiral center, that's a chiral center. What about this one though? Because we have 2 different R groups, but are they different? Wait. And so they're actually the same R group. So there's a plane of symmetry here. And so this one is not chiral. So this one only has 2 chiral centers. And so there are other ways to kind of show 3D. And so let's look at, so we've looked at this dash and wedge, drawing. And now let's look at the Fisher projection. So this is mainly used for sugars. This will probably come up later. But it's basically a way of writing a 3D structure kind of 2D. And so let's start with this formula here. So we have our molecule. And then, so now we want to orient it. For, holding our molecule. And so we want the chiral center to be on the plane of the paper. Okay. And then 2 bonds are coming out of the paper and are on the horizontal plane. And the remaining 2 bonds are going into the plane of the paper. We have everything oriented properly. And then so let's redraw this. So we're going to rotate our methyl group. And then we want to hold the molecule and rotate it until the hydrogen group is kind of perpendicular to the plane of the paper. So it should look something like this. So perpendicular to the plane of the paper. So I'm going to redraw this. So I just rotated, so our methyl group is still on top. So our hydrogen is more coming out now. So carbon, hydrogen. Now my chlorine is going to the back. OH is kind of over here. This could be going out as well. And so now we want to redraw this and kind of flatten it out. So anything so we're kind of looking at it like this. So my methyl is supposed to be the yellow one. Hydrogen's coming at us. And now I'm going to take it. So these two are kind of coming at us. So we're going to take it. Now I'm going to redraw it. So now it looks something like this, where my OH is coming out, my hydrogen is coming out. These are both, and this is why I recommend using a molecule kit, because you're looking at it like this. So now my methyl group kind of going back. Same with my OH, or sorry, my chlorine. And then now the last thing is we can just kind of flatten this image. Now we have our methyl group there, chlorine, hydrogen, OH. And so kind of the last thing is to assign priority. And so our hydrogen, if it is on, so now we can assign priority. So 1, 2, 3. Hydrogen, though, is on a horizontal bond. And then, so this is 1, 2, 3. So they're going clockwise. Well, this is horizontal, so this is S. Any questions about this? So let's finish up. So now the next question is, well, how do we know whether we have something that's chiral or not? And so to answer that, there is a special machine called this optical rotation. And so what you do, you put your compound in, then you measure the polarizability of light. And basically, if you have something that's pure of one racemic mixture, then it will show that with the light. So this is a polarimeter, so as a light source. And then this is unpolarized light. Then there's a polarizer in your sample, which contains your light. And then you get some sort of optical rotation, and then your eye can detect that. And so you can use these to kind of tell how pure then your racemic mixture is. So if it's non-polarized, then you have one or the polarized in one direction, then you have one or the other. If you have just a racemic mixture, then there'll be no polarization. And then so some terms to go along with this. And so this is by convention. So if there's a positive rotation, that means that it's clockwise. This is dextrorotary. Or if it's negative, then it's counterclockwise and laboratory. So kind of L for your left. And so the compounds will polarize the light by a certain amount, kind of depending on the compound. And so you could quantify that by the specific rotation of your compound. I think that's a good overview of the chapter. So Wednesday we'll do some practices. Oh, actually, one more thing. I forgot. Let's just go over this really quick. So this is, let's look at this Chemistry World article. Because the other thing that we're trying to answer is, well, why is chirality important? And what's interesting is that many of these biological molecules exist in just one chirality. And we've just been going over that, some of the difficulties in drug design is preventing this racemic mixture from occurring. So why is life chiral? Because honestly, it doesn't make a lot of sense if you think about it. And so this is why I like this article, because it kind of breaks it down really simply. So chiral molecules are just in one form. Sugars are right-handed, so we'll look at that if you stick on with 106, which I hope we do. Amino acids are left-handed, and DNA coils into right-handed helixes. So what causes this? And so kind of the big question is, if we came from this primordial chemical soup that is often hypothesized, you have all the basic building blocks, all our elements are there, but then how do we get this handedness? So it's a really interesting question. A lot of researchers have looked into it, have tried to do this selective crystallization. And actually this is what this one is talking about. So one of the theories is, you have a solution of a racemic mixture, and then let's just say, one bit starts to crystallize out favorably. Let's just say it's the right-handed enantiomer for argument's sake. And then now you kind of get, if you could imagine more right hands kind of stacking up on my right hand, you would get some sort of selective crystallization like that. At least, again, that's the theory. And one of the difficult things too is if we say that, this process took billions of years, no one was here to observe it. So, the best we can do is just kind of speculate. Yeah, and this study I think is interesting that Flag did in trying to make this chiral form or not, but it's still a big mystery. It's a big question out there. I just like posing it out there to my students so y'all can think about it, the origins of life, and all these basic things like chirality. It can have big implications for life and evolution. All right, let's end it there for today. Thanks a bunch. Thanks those of you that are alive. And I'll hang around on stream in case there are any other questions. Email me if you want to do office hours appointments. Otherwise, let's plan on doing some practice on Wednesday. So thank you all again and have a great day.
Gotta focus on yourself, on your faith, on your dreams, on your mind, on your health, yeah. You gotta
Wow.